All right, here is that example. That looks fun, right? Okay. It says, and very simple problem statement, find the power absorbed by, one, the resistors, like all the power absorbed by all the resistors in the circuit, the power absorbed by the current source, and then the power absorbed by the voltage source. Okay? Simple enough, right? What do you think you might want to do first for a messy circuit like this one? Because that looks kind of messy, right? You might want to redraw it in some way, but I have a strong suggestion that even before you start redrawing it, identify your nodes, and my favorite way of doing that is to use some color. Okay? So I'm going to start identifying some nodes here. I'm just going to start here and start identifying a set of nodes right here in the middle. And the way you do this is you drop a highlighter on the wires and you try to go to all extents before you hit any kind of a circuit element. Like you go as far as you can in every direction before you hit a circuit element. And what you will have done as you do that is color in one of the nodes. Okay? I can do that again. Let me choose yellow here, and I'll start coloring this node over here. And it doesn't matter where you start, but you do have to go to the furthest extent any direction that you can, right? So here, you know, these kind of represent little hopovers, so it doesn't connect right there if you see a little symbol that kind of hops over the wire like that. It does connect if you see like a little dot that is shown like that right there. Actually, you know, we generally, even if you don't show a dot, you can assume that you've got a connection point, at least in the standards of how we tend to draw circuits in this course. All right, so we keep on going until we reach all the way to the extents and wherever we hit circuit elements. I didn't finish up here, so I'm going to keep going around there, all the way up to that voltage source. This basically is more wire that goes over there, so I keep going till they hit that circuit element. And then lastly, I would go around here until I go back to that where that 8 ohm resistor connects. And I think that did me good in terms of identifying that whole node, right? I just started anywhere in the node and I tried to draw as far as I could until I hit any one of my circuit elements. Okay, so now everything yellow is another one of my nodes. Let me get another color in here now. I'm going to use this aqua kind of color, and let me identify some of these you know, wires up in here. Okay, so I'm going to again go as far as I can until I hit circuit elements. Okay, and I think that identified all of those. Do I have any more nodes? Is there any stuff that's not colored right now? I've got one more node over here. So any difficulty kind of tracing along with what I did right there? All right, good. Now, what I'm going to typically do once I've got that drawn like that is I am going to probably try to start with my sources if I can. I'm going to put those on the left. That's the way a lot of circuits tend to be drawn. You don't have to, but that's one way that you can draw them and maybe make it feel more familiar to you, right? So I'm going to take my voltage source, my 6-volt voltage source, and put that over here. And I'm just going to show a couple of terminals that I just start off sticking up and down like this, and let me go ahead and start coloring them also. The positive side of the 6-volt source goes to what color node? Yellow, right? And then the other side goes to green. Okay? So now let's identify other things that go across from yellow to green. Does my other source, I have a current source in there also, right? Does it go from yellow to green? Okay. That means that I can draw it in there in parallel with the 6-volt voltage source. We'll put it in there like this, 3 amps. Now, what direction should the arrow point? Okay. You'll notice it goes from yellow toward green, right? So I need to be consistent with that as I draw it in here, from yellow toward green. And that is also going to be colored yellow here and green down here. All right, do I have any other circuit elements that go across from yellow to green? Okay, that 8 ohm resistor also goes across there, so I may as well put that on here as well. It's an 8 ohm resistor that goes across from yellow to green, like this. All right. Anything else that goes across from yellow to green? Okay, so I would say at this point, we don't have any other single elements that go across from yellow to green, but we have combos of things that go across from yellow to green. One of those, we'll notice that we actually have a large number of things that are connected from yellow to aqua. Do you see that? So why don't I show across the top up here an extension of this yellow node and identify all of the different little pieces that go from yellow to aqua, right? So there's going to be like a little resistor here. It looks to me like there's actually 4 different resistors that go from yellow to aqua as I evaluate all of that right there. And I can label all those if I want: 4 ohm, 11 ohm, 12 ohm, and 10 ohm. And those all connect up to a common node right here that is that aqua color. With me so far? Now, does the aqua colored node connect with anything else? Or did I get everything that came off of my aqua colored node or not? There's 2 elements that go from aqua to green, right? So I can draw those if I would like. Let me show you a way of kind of really emphasizing that because the 5 ohm and the 15 ohm both connect to the same pair, right? They are in parallel, and so even though I didn't have to show this little leg in between these 2 things, that helps some people visualize that I've got a set of parallel resistors here with the 5 ohm and the 15 ohm as well. Okay, so I can come back in and keep my color scheme going, right? That's all green, and this is all aqua. Am I missing anything? I haven't really done these over here, right? The 1 ohm, the 9 ohm, and the 7 ohm. Where would those go? They come off the yellow, and it looks like they each connect to the yellow. So let me go ahead and extend my yellow node out a little bit further, and I'll do just like I did with my other ones and identify each of these elements that's connected off of that yellow node. This will be the 1 ohm, this will be the 9 ohm, this will be the 7 ohm. What do they connect to? Yeah, they do connect on the yellow side, that's true, but what else do they connect to? Each other on that purple node, right? So I can draw that down here. Is that all the places that the purple node connects anywhere? Yes. Okay, now some of you are looking at that circuit and going, that looks weird. What do you say looks weird about this circuit because I think I'm done redrawing it, right? I think I've got all my elements, I've got them all connected across the same pairs of nodes, right? Magenta appears to be useless is the comment that's just made. Okay, why is that? Doesn't connect back to anything, right? Let's say that, just for hypothesis sake, what if I tried to show a current that flowed on that leg? It has no place to get back into the rest of the circuit, right? What do I conclude then? That current doesn't exist, right? And there's no energy supplying elements over in that circuit that is between the yellow and the magenta over there. There's nothing that would push current or voltage or anything over there. So basically, all of this stuff over here is irrelevant. That makes sense? So I can just eliminate it, and it won't change anything that I am trying to find for this problem. Okay? We okay with this idea? Okay, so that means I can really just focus in on the left half of this circuit. What I'm trying to do is find the power that's absorbed by the resistors. What's the first step, you think? Find an equivalent resistance for all of these resistors connected, okay? And I would identify and say probably where I want to look is where do all of these resistors connect to the sources, right? Kind of imagine there being 2 terminals right there and saying I want to know my equivalent resistance across those two terminals. Do you agree with that? Okay, where do I start with that process? Okay, tell you what, I'm going to redraw the circuit as I go along, and I think this is a really good idea for people who are kind of still beginning, even for people who aren't still just beginning. It's a good idea to do sort of a redrawing of the circuit for each one of the simplifications that you make as you go along, right? So here, this is an 8 ohm resistor. And the step that we're about to do, I think, is that we are going to take all of the stuff between the yellow and the aqua and turn that into an equivalent resistance. Do you agree with that? That might be a good step? Okay. Also, I could take everything between the aqua and the green, and I could convert that into another equivalent resistance. Right? So let me label those as REQ1 and REQ2. And what is REQ1? Okay, it's going to be 1 over 4 ohms plus 1 over 11 ohms plus 1 over 12 ohms plus 1 over 10 ohms. Okay, and because I trust that all of you know how to calculator, I am going to give you this result. Okay, when I did this out, I came up with 1.9075 ohms. Now what about REQ2? Yeah, you have two choices about how to do this one because you've got two in parallel. For now, let me just use the same technique that I used on this last one. 1 over 5 ohms plus 1 over 15 ohms. If you do that, what I got for this is 3.75 ohms. What was the other choice? Because I mentioned there's two choices. What's the other choice for how you do REQ2? You could do the product over the sum, like I showed you in that one little optional piece. Okay, what's the next step? You can just add those two together, REQ1 and REQ2, and even though I know it seems a little tedious, I'm going to go ahead and redraw this circuit again. What we're basically doing in this step is we're adding together REQ1 and REQ2 to make REQ3. So what that would be is just 1.9075 ohms plus 3.75 ohms, and that ends up giving you 5.6575. What's the next step? What we're going to do is we're going to combine in parallel my 8 ohm and my REQ3. Okay, so let me redraw that circuit. 6 volts, 3 amps. Okay, now we're down to just one resistor. And a lot of times what I'll do in my notation, this is optional of course for you, but on my last step I a lot of times drop the numbering and say that is my overall REQ. Right? So, and again, that's not a standardized bit of notation, but that's a lot of times what I do. Okay? So what do I do now to find REQ? It's parallel. Since I did using the plain old, just reciprocal of the sum of the reciprocals the last time I had a pair of resistors, this time let me do the product over the sum, just to show you the other way that you can do the same idea. Okay? So this is just going to be equal to 5.6575 ohms times 8 ohms over 5.6575 ohms plus 8 ohms. And what I get when I did that was 3.3139 ohms. Was that what I was looking for? Not quite, but it's a really important step along the way. Why? I'm looking for the power absorbed. Let me ask you this. If you know a resistance value, what else do you need to know the power that it absorbs? Either voltage or current. We can go directly from either one of those terms, right? Do we know either voltage or current for REQ? Okay. What do we know? We know there's 6 volts across it, right? we know that essentially we've now reduced down to kind of more or less just the top node up there and the bottom node down here, right? So if I've got 6 volts across that node held by that 6-volt source, that's the same voltage that's across REQ. Okay? So that means that the power is just going to be equal to 6 volts squared. Remember, the formula I'm using here is V squared over R. So 6 volts squared divided by REQ, which is 3.3139 ohms. And so what that ends up giving me is 10.863 watts. Okay? And so that's the answer to part A. Was there anything else I needed to do? I want to know the power absorbed by the current source also. Well, you want to know something cool? I didn't need to do any of that to find that value. Why not? I know the current and I know the voltage for that element. The voltage source is holding the voltage across the current source, and the current source is ensuring that a particular amount of current is flowing through it. So for that element, the current source, I know both the voltage and the current. How do I find power? Let me do this as well, because I can go down into showing this one. I know that the voltage is actually this way across that current source, and the current is flowing from positive to negative. Does that mean that I'm having power absorbed there or power supplied by the current source? Absorbed, right? Anytime you see current flowing from the positive to the negative of an element, that means that you are absorbing power, not supplying it. Okay? So that tells me that the power for the current source, let me denote that as P sub CS. How about that? The power for the current source is going to be equal to just 6 volts times 3 amps, which is just 18 watts. So that's the answer to part B. What was part C? What's the power absorbed by the voltage source? Okay? Now, there's 2 different ways you can do this. One is if you can find voltage and current for that voltage source, then you can find power. So we do that one first. How do I find current being supplied by the voltage source? I can do a KCL, but there's probably one step I should probably think about doing first, right? And that is to come up with what is this current that flows through REQ, right? Let me just name that I REQ, okay? You just use Ohm's law, right? Ohm's law says that I for REQ is just going to be equal to what? The voltage over the equivalent resistance, 3.3139 ohms. And if you calculate that, that winds up being 1.8106 amps. Okay? Now that's the current that's flowing on that leg through the equivalent resistance, right? How much is flowing on this leg right here? 3 amps. It's a current source, right? So that's going to be 3 amps. So what does that mean as far as the current that flows up here? Okay, I'll call that I sub Vs. That's the current supplied by the voltage source, right? The current supplied by the voltage source is just going to be equal to the 3 amps plus the 1.8106 amps that I have flowing through REQ. So this ends up giving me 4.8106 amps. Is that what I'm looking for? Not quite. Almost there. What else do I need to do? The power for the voltage source is going to be equal to its voltage, 6 volts, multiplied by the current that it has to supply at that voltage, right? 4.8106 amps. Now, before I actually write anything else here, is the voltage source supplying power or absorbing power? So, if what I'm trying to do is specify my powers in terms of absorbing, what do I need to do? I need to make this a negative value because I'm trying to express it in terms of absorbing power as opposed to supplying power, right? And I'm seeing there that the current that I'm finding, this IVS, flows out of the positive terminal, right? That means by default it's going to be supplying power. If I'm trying to express that in terms of absorbing power, that's where that negative sign comes from. That makes sense? All right, so this winds up being 28.863 watts. And that's the answer. Yeah, negative. Very sorry. Negative 28.863 watts. That's the answer to part C. Now let me ask you this. Without having to go in and find that current, is there a way you could have known what that power had to be? Okay, you might remember the fancy term that was in some of our previous notes, Teligens's theorem. You remember hearing that? Teligens's theorem says that the sum of all of the powers in your circuit has to be 0, right? And again, you have to kind of decide which direction you're taking to be positive. So the sum of all the powers absorbed in your circuit had better be 0, right? Well, we're absorbing 18 watts in the current source, and we're absorbing 10.863 watts in the resistors. That means we better be absorbing negative the sum of those two out of the voltage source. Is that how it works? 18 watts plus 10.863 watts gives you 28.863 watts, right? So yes, it does work that way as well. Okay? You follow that? All right, so that's kind of the end of that example problem. Any questions before we get into the lab? Yes? Yeah, so basically the question was, can I explain one more time why I knew to put a negative right there, right? So here's why. I want for this power to be positive when it's absorbing power, when that element is absorbing power. I want that to be positive. I know that it's sourcing 6 volts and it's sourcing 4.8106 amps at that voltage, but I can look up here and say IVS is positive going, that is a positive value and it flows that direction, meaning it has current that's flowing that direction on the 6-volt source. And the 6-volt source has its polarity oriented so that the positive is upward. Whenever we first looked at our power scenarios, when you have that, when you have a voltage that is positive on this end and you've got your current flowing out of the positive side, that means this is supplying power. But I want my P that I'm calculating here to be positive when I'm absorbing power, so I have to put that negative sign in there to get that. Another way I could have done it is I could have just put a note down here that says P sub Vs supplying and not put the negative sign and then dealt with the negative sign in a subsequent step, right? Or, interpret my results so that I answer the question that's asked. Does that make sense? So that's really the only reason the negative is there. All right, good question. Other questions? Okay, we'll call that good.